is essentially, it's actually, in a way, I think it's pretty good timing with where we are. I feel the need to crow. I know I can't abuse his presence here, but
He'll be back in later.
So essentially the idea is there was a time when this concept of energy was not completely, deeply fleshed out. And there were two independent directions of research that had been going on for quite some time. And we talked a little bit about those in 212. The idea of specific heat capacity and conductance and heat transfer. We just immediately went to that being energy and talked about it in terms of joules and whatnot. But there was a time when that context was not very well laid out. It was very ambiguous. What the hell is heat? You got to know what energy is, because this whole idea of work and mechanical kinetic energy change, that's very easily derived and expressed analytically or mathematically. So the two worlds were essentially the world of heat and the world of energy. Now, primarily, the people doing heat-related research were what we would call chemists, and they were focusing more on interactions and chemical reactions and properties of matter specifically, much less concerned with broader rules of interactions, because they thought heat was a substance. So it kind of makes sense, right? You're a chemist, you're studying matter and properties of matter, types of matter. Of course, you'd be trying to understand this fluid concept of heat. That makes perfect sense. Now, to this end, Joseph Black, among others, had established a technique to compare relative heat absorbance properties for different substances. And the idea is if you take a system of some amount of mass and it absorbs a certain amount of energy, maybe you put it under a flame, then the idea was that the temperature is going to rise from some initial temperature up to some final temperature based on how much heat, invisible fluid, if you will, is being absorbed during the transfer from this flame, if you will, into the system in question. And so the idea then was that if you measured the temperature, or I should say the measured temperature change for this mass should be, and essentially is directly proportional to the physical quantity of heat that's absorbed and inversely related to the mass of the system. And the proportionality that relates the two, we've got Kelvin Celsius units, we've got heat, joule unit, or I should say calorie units. So heat as a quantity was originally at one point thought to be caloric, from which we then say this heat absorbed is measured in calories. So this was essentially the idea. And there's a proportionality constant that relates the two. So for a certain amount of heat absorbed, there's some constant here, and I'm just going to make it a big C for now. I'm going to move it around and adjust it. But this was essentially the idea. The direct relationship between the flow of this substance and then what you observe as a change and how it relates inversely to mass. Now, when you rearrange this thing, one could say that we could calculate the heat absorbed by some system by measuring that system's mass, warming it up or cooling it down, measuring the observed temperature change, and using the physical property of that particular substance that we'll have to figure out how to measure, or I'm going to use a lower C, not a large C. So this big C is just a engineering fudge factor concept, if you will. My daughter says to me this morning, she's eating Nutella with toast, and I'm thinking about fudge constant. And she hands me the toast and says, "You never bite, Daddy," so I'm eating toast. She goes, "Daddy, what you eating?" "Nutella, chocolate. Where'd you find it?" And I'm supposed to say, "A dog dropped it." "Why'd he drop it?" But it's our morning. Okay, it's a fudge constant, but we say normally we arrange it 1 over this C constant, which we call this little c. And this little c is the specific heat capacity. So again, it's specific for a given substance. And it's the capacity to store heat for a given amount of temperature change. Or, if you will, required energy necessary to manifest a certain temperature change, given the system's information. So this is sort of the idea then. Now the question is, okay, well, all these substances have this physical property, specific heat capacity, which will be related to this inflow or outflow of invisible liquid heat or caloric. And ultimately, one thing that we can measure, temperature change, that's different before and after that energy, or that heat is absorbed. Now, here's where we're going to take it, and I think we did a lab like this in the past. Originally, the idea was best thing to work with. I have to move my energy thing over here. One of the more easy substances and ubiquitous substances in the world, water. We're all made of water, all food's got water in it, everything's about water. So originally they said, well, given lack of any other information, let's start with a reference. And that reference is, essentially, if we define heat quantity in calorie units, where, using water as a reference, 1 calorie of heat is the amount of energy, the Q, that's associated with raising 1 gram of water by 1 degree Celsius. Again, this is pre-SI, pre-Kelvin units, so Celsius was, at this point, the standard metric unit of temperature. Well, based on this then, we could re-express it and say, oh, well, the heat capacity of water then is 1 calorie, and I'm going to put some decimal places in now. Again, there's another unit in there. Calorie per gram degree Celsius. In other words, we establish a baseline for the unit of calorie, and simultaneously this physical intrinsic property, specific heat capacity, we just established the baseline at 1. So any other heat capacity we measure, we'll measure it based on the standard of calories being equal to 1 gram, or one unit of calorie required to raise 1 gram of water, 1 degree Celsius. Now in SI units, well, we don't have SI units, we got to deal with that one, so we'll leave it alone for now. But I will say that this sort of corresponds to 1,000 calories per kilogram degree Celsius. Okay, so typically in SI units, at least we'll use kilograms. Now, to this end then, comparison of relative temperature change between water and any other material of different temperature. This will yield what the specific heat capacity is for a different substance. Okay, so that was essentially the idea. So you measure, take a hot object, put it in cold water. The hot object, cold water, they eventually reach the same temperature as heat flows back and forth between the two, and you reach this thermal equilibrium. Well, the relationship between the temperature changes will be directly related to the specific heat capacities, all other things being equal, with the assumption that the same amount of heat that flows out of one flows into the other. So, cold water of some mass, hot object, same mass. Put them together, they reach some, great to have them with color. Final temperature. And the idea then is that the heat capacity would be related, again, same mass, as long as we can cancel out the masses, and the heat capacity should be related of the substance, of the unknown, should be related to the heat capacity of water times the ratio of the temperature change the water undergoes, divided by the temperature change that the substance undergoes. I'll sample. This is the sample. So that was typically how this heat capacity idea was measured. And the technique that was used to do this first of all, was based on the assumption of the flow of a conserved quantity of heat fluid. And we refer to this type of a process as calorimetry. Okay, and I'm pretty sure we did a specific heat capacity at last quarter. I'm sure we did. Okay, so this is the calorimetry technique. So just a quick reminder. So this is essentially how they did it, even before a necessary understanding of what this idea of heat was. Now, from the energy perspective, then, the idea was essentially from an electronic perspective. Let's start there. This is where electric potential becomes a particularly cool thing when you start talking about making the transition from vector field quantities like electric field, and we make the transition into just looking at things in terms of energy as it will ultimately go into electronics or electricity. And the idea then is something like this. Oh, my pen's dying again. So we take some material and plug it into some power supply. Plug it into some power supply. Maybe we have a potential difference of some value, 9 volts or whatever, between the two ends of this capacitor, or I'm sorry, of this conductor. So we'll assume it's some sort of a conducting material. And let's think about what might happen. As electric charge, and it's backwards from how we would normally think about it, but if I were to take an electric charge at one side and have it flow to the other side, so the Q comes out the other end. So Q goes in one side, Q comes out the other side. Here's what we can say about what this electric charge undergoes in this process. The electric potential energy on this end is equal to the magnitude of the charge and whatever the potential difference is here. So let's call that initial. When it gets to the other side, because it's now in a different potential, electric potential than it was where it started, I don't have to worry about this even being an electric circuit. We're just looking at electric charge moving from one electric potential to another. Okay, so don't even worry about what you don't necessarily know and all the questions of resistance and inductance you don't necessarily need. You don't need it at this point. So when it comes out the other end, it has a final potential energy, electric potential energy, which will be related to Q times whatever the potential difference is when it gets there. And this potential, or potential when it gets there. So that could be 12, this could be 8. That could be 1,000, this could be 991. Or whatever. As the electron goes, or as the charge goes from one side to the other, the change in potential energy will be equal to the final minus the initial, or if you will, Q V minus V plus. Right? There's your delta V, if you will. It should go from one side to the other. Now, based on our understanding of what electric energy does, work involved, conservative force, as the charge goes from one side to the other, again, no deep smoke and mirrors here, it's pretty direct. The work required to move that charge from the positive end to the minus end is equal to minus the change in the electric potential energy. Or, if you will, Q V plus minus V minus. just call it Q minus Q delta V. It's a positive charge. It goes from positive high to low electric potential. And energy is lost in the movement of that process as positive work is being done. So Q's positive over here, and we're going from high to low. There's going to be a drop in electric potential energy as work is performed to move that charge across. Just energy. Cool thing, it's conservative force, electric field. How do we know there's an electric field? What's the electric field in a conductor? What would Gauss's law say it was?
Inside
a conductor. Zero. But the assumption of that is charges are just present. When charges are moving around, you may not be able to draw a Gaussian surface with no charge inside if the charges are moving around. For instance, flowing along. So whenever you have a movement or dynamic charge movement, you don't assume that the electric field is zero inside a conductor. But there's a more direct way to understand that. Electric field is just minus the change in the potential difference. In this case, it would be in the x direction, if that's our x direction. So as we go from a high to a low voltage, as we go from one side to the other, the potential difference, as it decreases from one side to the other, the relative drop in electric potential will be corresponding to the electric field. So there is, in fact, an electric field necessary to move the electric charge across. And that makes sense, right? I mean, it's not just going to do anything on its own. You need disturbance to get change. So, of course, we'll put in the I direction here, I suppose. Now, let me ask some heuristic questions. There's no power supply, and thus the potential difference, there's no potential difference between the two sides of the conductor. A wire, whatever. And by the looks of it, we don't have the stuff here. Every time we're not here. It might be in one of your kits. We'll get to that, I guess. So, if there's no potential difference, in other words, constant electric potential in a wire, how's the charge going to flow in that wire?
If there's no what?
There's no power supply, if you will, hooked up to the wire. Okay. I don't plug this thing in.
No current.
There's no current, there's no charge movement. You can think of it as electricity or current, charge movement. Charge isn't going to flow. One way of, what's that?
It just sits there, right?
Yeah. Well, we might say partially, why does it sit where it sits? Why is it evenly spread out?
Because they repel each other.
Okay, so all the charges reside on the outer surface?
Right.
Even if it's neutral?
If it's neutral?
Yeah, if there's no extra charge here. All right, just a wire. I'm not talking about one that I rubbed on my ass to give it electric charge. I just mean it's here. Okay, let's not make it any more complicated. What else is inside besides the other electric charges, the negatives? All the positive charges. So all of the electrons, when there's no excess, if you will, all the charges evenly distribute throughout the entire material because every atom, if you will, is neutral inside. Okay, so that's a nice thing. Pretty straightforward. So there is a basic attraction between the electrons and their parent atoms. Right? So you got an iron atom, and whatever electrons it has, it's just going to sit there unless something kicks it off. You need some energy to move it, otherwise it's just going to be there. Okay? In order to physically move electric charge, it requires that there's enough force and enough energy to physically displace it from its own atom. Right? Otherwise, it's just going to hang there. You've got to have enough to move it off. Makes sense, right? I can push on a book, but if I don't push with enough effort, it's not going to go anywhere. You've got to give enough to get it going. Okay, so you've got a few things going on here. So inside the conductor, you got to understand that you've got this basic attraction, the positive, negative charges, as well as the repulsion. You've got things going on there. And the result of this is there is a basic electric drag. There's a basic drag force, if you will, or a drag that holding the electrons and keeping them from just flowing, say, at constant velocity. Right? You don't have to have a force to move at constant velocity along. But it doesn't happen because there's a basic friction, if you will, that holds, or attraction that holds the electrons to the neighboring atom, that holds the charges in place. Got to have some force to push them along. Till that happens, it's just there. Now, kind of like air resistance, here's something sort of interesting. I'll try to take my word on this, but I don't have any way of justifying it. You can use a little bit of force. You create a little bit of an electric field, and you can displace or move a few of the electrons, or a few of the charges, and they'll start to move. If you put a little more energy, a little more electric field, then you can push more of them across. The bottom line is the more charge that flows because of their own mutual repulsion, the harder it is for them to physically flow, the more energy that's required to push them along. Said a different way, if one charge requires a joule of energy to flow from one side to the other, moving two charges would require 2 joules of energy. Moving 3 charges would require 3 joules of energy. So there's an energy price to move the charges across, and really that price is work, but it's also, in a sense, overcoming the attraction and overcoming the drag, the friction